So it's my pleasure to introduce Jeongseok Oh from Imperial College, and he's going to be talking about counting sheaves on Calabi-Yau fourfolds.
Thank you very much for introduction and invitation. Yeah. I come here every World Cup year, so just maybe the final is Saturday.
What's that?
Final is Saturday.
The final?
The final of
Yeah.
France and Argentina, right?
Yeah, I guess you were here the last time. Yeah, that's right.
Don't blame me. I want to talk about how to make some invariant, so-called Thomas invariant or Calabi-Yau fourfold. So we begin with the virtual cycle. This plays role of a fundamental cycle, fundamental class of non-smooth space. So over this cycle, we can integrate on it to produce invariant. This will be in this case, this will be Thomas invariant. Okay, so the M possibly singular space. For instance, in practice, in our example, will be modular space. Then we'll denote our virtual cycle by this. This is some cohomology class or Chow cohomology class of M. So they are related. Sometimes we take for homology here, but degree could be twice of this. So yeah. So once we have this, as I advertised, over this cycle, we could integrate cohomology class that produces a number called invariant. And for instance, if X is if M is modular space of curves in X, and that produces invariant of X, and if M is modular space of vector bundle or sheaves, that produces AT. Okay. The simplest, I want to introduce the simplest case we can make, where we can make this virtual cycle. So I'm going to define what's cut-down model. M is data consisting of smooth space and a bundle, vector bundle A, and a section of E, vector bundle E, such that its zero of this section is our modular space M, our space M. So in picture we can draw like this. Yes, so we have space and bundle on it, and we have a section S, and then it's zero, or it's a closed subspace over A. That is isomorphic to M, then we call this 3D data as cutout model of M. So like this bundle on A gives rise to Euler class of E. So this is a class inside the Chow group of degree dimension A minus rank E after of A. Then Fulton Macpherson constructed a class. So given this all this data, Fulton Macpherson constructed a cycle depending on bundle and section on the Chow group over zero set of S in this case now M, and if we denote this by I, then we have push forward morphism between these two Chow groups. And what they constructed is there is a cycle which to this Euler class. So this class is defined on the ambient space A. So what they constructed is a class inside the M, which push forward to Euler class. Then with this cut-down model, we define a virtual cycle. So if M comes equipped with this cut-down model, then this is defined by this Euler class. So the conclusion may be, so virtual cycle is some localized means this is some push forward of some smaller space. Anyway, this is the Euler class. Now to go next stage. So this is defined only when we have cut-down model of M. So what if we need some ingredient. Also, so we need another data, more some generalized data of this cut-down model. That is called perfect obstruction theory. So to explain the perfect obstruction theory, we may need some preparation. So we first define what cotangent complex. Very general case, this is, as far as I know, this is defined by Beruzzi. But here, I only want to explain what we need. This is not precise definition. First of all, choose an embedding, closed embedding of M into some space N. With defining ideal I. So I use different notation n because I want to emphasize this is not from cut-down model. So you choose any embedding m into n, then
And it's smooth.
sorry, yes, and then it's smooth. Then we have this sequence. Then, of sequence of OM modules. Here we have a Schiffer-Keller differential of n is equal to n. So, since this could be singular, this need not be locally free, but this is locally because this is smooth. So anyway, so this two-term resolution, although this may not be locally free, but anyways, let me denote this by LM, and this is and so this is really complex on the derived category of M, and this independent of embedding. Now I want to define what's perfect obstruction theory. The notion of defined by Behrend-Fantechi. So this is in some way this is some generalization of this cut-down model. So this definition of the perfect obstruction theory consists of the Balanced data. First, we need two-term complex of vector bundles. This is complex of vector bundles on M. So this is some element in derived objective derived category. The difference between here is this is also two-term, but this may not be locally free. And also, we also need data morphism in derived category to M, and Behrend-Fantechi called this two perfect obstruction theory of M if this morphism in homologies. This denotes degree. So the zeros of homology if by in this isomorphism. And this is surjective. If that is satisfied, then this is called POT. And one remark is, as we've seen, the zeros cohomology of this is Schiffer-Keller differential of M. And this is yes. So POT is some like a complex with zeros cohomology Schiffer differential. But there can be something more than this the cotangent sheaf. Conormal sheaf. But there's something more make this part to be locally filled. That's the definition of a perfect obstruction theory. Then what's good of this perfect obstruction theory is this is pure T. Yeah.
So normal part, the I mod I square is the -1 degree?
Yes,
Oh.
minus. So if this is pure T on M, then for any point in M, geometric point in M, there exists a neighborhood of X such that this is U is cut-out model. On which you described as 0. Yes, this is such that and this M has cut-out model satisfying this. Let me write it first and explain later. EM restricted U is quasi-isomorphic to this two-term complex, and also this the restriction of pi morphism in their category is equal to if we denote if J is we denote the ideal shape of this closed embedding to be J, then we have this morphism. This is given by differential. And this is S. Anyway, so I mean by this two morphisms. Yeah. Great. Yeah, I want to explain something a little bit more. Because this is first of all from morphism S we have this differential between tangent spaces of A and B. If we restrict this to U, which is 0 over S, then this part will be canonically decomposed into 0 part and 5 part. So this morphism is dual of this projection. If we project into second component, then the first row is the dual of this morphism. And another way of writing this section S is as a modular homomorphism. So this is A OA to E. So this dual of this induces homomorphism of duals. Its image is J. So this is the meaning of J. So step us through this. So whose coconut is structureship of U. So this morphism now, if we restrict it to M, then this morphism gives us this. And this is really differential. So if we have a function in J, then we take the differential of that function. Any question of the meaning of this perfect absorption theory? So let me say, if we have perfect absorption theory, then we can say locally we have local cut-down model. So that locally we can define this means, first of all, from this condition, quasi-isomorphism condition, what we know is rank of dimension A minus rank of E is equal to rank of E0 minus rank of E minus 1. So here, that's this two. And we denote this number by rank E. Then because this says if we have perfect absorption theory, then we have local models of and pure T. This means it exists a cover, open covering. Such that on which this is defined. Then what Behrend-Fantechi did or independent method, different method, Lithian also proved a similar thing, but Behrend-Fantechi did this. It's to define from perfect absorption theory, Behrend-Fantechi define virtual cycle in this way. So it says virtual cycle is somehow gluing of all classes. I want to give some examples. So first, Graham invariant is, we we start with the smooth projective variety x. So that I'm considering field C complex numbers. And then the modular space is the data of curve and path. So this curve and map into map to x. So this is some collection of these two paths of mapping into x. In this case, if we pick one point P, which is data of this curve and map, and if this is if C is smooth and F is embedding, then what we know is tangent space at M is defined as isomorphic to Jero's shift homology of normal of x into x of C into x. So this says which dual is just this is dual. In this case, we can construct there is a natural POT of M such that every point Jero's cohomology at P is equal to that, because this is part of the it should be this way. And what I really want to say is minus one cohomology is one of this. The difference of rank is constant. Difference of rank constant because the shift cohomology on some dimension 1 space. So other than 0, 1, everything vanishes, and because all the characteristics should be constant, so that means difference of this rank should be constant. So that means this is really perfect, because the rank, so that's almost equivalent to this should be two-term complex of vector wonders. So yes, and so this POT gives some perfect obstruction, the virtual cycle, and over the cycle the integration define complete invariant. And second example is invariant. Here we are considering Fano or Calabi-Yau three-dimensional complex manifold, and then we are interested in moduli of a sheaf or stable sheaf on X. Then if we take point P, known the cotangent space at P. You guys move to next one. So the tangent is x1, cotangent is h2. Then similarly, we have TOT. Such that, of course, by definition, this is sorry, yeah, next one. And again, the difference of this because the stability condition implies rank of x0 and rank of x. So rank of x0 and rank of x3 will both are constant. And again, since this is three-dimensional object, to preserve this, because this Euler characteristic of this home of E that should be constant, that means the difference of this numbers, rank of this number, constant.
Where are you using the Fano or Calabi-Yau?
Calabi-Yau, the definition of stability in this simplicity, and so this is always 1. But if we have a Calabi-Yau condition, then duality says this is also rank 1. And Fano says this is 2.
And so if it's general type, the x3 is the problem.
Yeah, so this is not defined on general. Okay, do you have any questions so far? You not want to stay?
Sorry, so just to summarize what you've done so far, so M is some moduli space of Sheaves, which is not smooth usually.
Yeah.
And this procedure of using a perfect obstruction theory produces something like a fundamental class, even though M is not smooth, and you can integrate homology classes over that fundamental class to get numbers which are sort of like counting Sheaves on X. Okay.
If there is Calabi-Yau threefold, these two numbers, the rank of these two are same. So this defines class of dimension 0. So we don't have to really integrate both homology classes over this class. You can just count degree of the class. The most famous degree.
So then that's just like sort of the number of stable Sheaves.
Yeah.
In some sense.
Yeah. Cool. Okay. So again, we are interested in stable Sheaves. Next. Then still we have something, so even though this is not perfect obstruction theory, we have something like this was a voltage in derived category from EM to LM such that the iso and the surjective, but this is not flexible vector bundles. So this is not POT. Okay. Yeah, let's see. So then what is this? So this implies sorry. So at point F, so point P, this is again 1, and this is 2, and no, this one, this one. So, and there's no like all others are. So we have this such that so this satisfies all of these things. Okay. Then by this the stability condition and Calabi-Yau condition says rank over x0 and rank over the 4, these are over 1. So the alternating sum of these is constant. And let's do some more observation from cell duality. So the goal of now this talk is defining virtual fundamental class with this non-perfect obstruction theory. We observe by cell duality says x1 is isomorphic to this is dimension of our space, and this is one they are exchanging and dualizing shift. And now since this is trivial by Calabi-Yau condition, this means these are true to each other. And similarly, we have this, and this says this is self-due. So by this observation, what we call this again is represented by this 3 represented by vector bundles of this form. So you can just imagine this roll over the next one, and this is x3, x2. Then this self-duality gives some this isomorphism, and this says this place could be the dual of this place. Or maybe it's better say okay. So
The composition is 0.
yeah, composition is zero. Because it's complex. And yeah, the point is, as point varies inside of a moduli space, this X group may not be vector bounded. So this rank of each term can be changed, but we have some complex of vector bundles whose cohomologies are X. Then similarly, from there, we obtain some local cutout model, as how we did it in the first part of the show. Or we better to say axis P with this notation. There is neighborhood U such that now our local cutout model look like this. This part are all same, but we need some more data. So from Q, we also have some isomorphism 2, and we also need some isotropic condition. When we consider this Q as quadratic form, so this isomorphism gives rise to this non-degenerate quadratic form. So we move this here, and since S is a section of here, Q of S is an excess. If this is 0, so the condition is this is 0, and of course means 0, such that define TJ E and this is very isomorphic to enjoy. This is quasi-isomorphic. So again, so what I want to say is we have local model that covers this, and what's good in this case is the rank is even rank E, the middle term is even. We have Edidin-Graham. By curve for the class inside Chow of rank of dimension of E, dimension of A minus 1/2 rank of E. But we need some coefficient. So we actually any integer being containing 1 over 2, that's fine, but for convenience, I just cube. So as we've seen from notation, this class has this property. The scale of this is what we did is we can construct. Similarly, we can construct some class inside U. The same. Let's not this number of virtual dimension. Then I push forward of this embedding. Sorry. So this should be A. Because now E is defined on A, and so we need some coefficient. What we did is there is some class inside the 0 of S that mapping to Edidin-Graham class. Then our main theorem is we can glue them to define inside the child group of M. So this says this class is virtual class is gluing of Edidin-Graham class. Okay. Any questions so far? One point. So this is only defined when E is E. So when E is above, then we define this to be just. Maybe this is useful for the next. Yeah.
So, my intuition for the Euler class, the usual Euler class, like when S is a regular section, so it's zero locus is smooth, it's the fundamental class of the zero locus. Is there any such intuition for the square root of the Euler class?
Okay, thank you very much for the question. So there is some nice intuition. So we have this bundle with quadratic form, then that gives locally we can write this way. So this is sum of bundle plus its zero. So if we have section S, so then we may assume this could be decomposed into two parts. So Edidin-Graham class is we can understand this as the Euler class of one of those.
I see.
So this localization is the usual. We have usual the Fulton-Macpherson localized class, but we can further localize with S2, so-called the cosection localization. So this is Kimley's cosection localization. This is the class. Say why this is real number. First, we have gauge theory definition. Let's assume that let's start with this quadratic bundle. Start with this quadratic bundle, then we can find which is a subbundle or real subbundle. E such that the dissection of this quadratic form is a metric, and with this decomposition of E as a mirror bundle, I times E. Then our is and Edidin-Graham showed their class in homology. So they defined the Chow homology, but in homology, because this is defined only on homology. Actually, this is oriented mirror bundle, so that Euler class is defined. So then Edidin-Graham proved this. This is an obstruction bundle coming from the body case. And one remark is Borisov-Joyce constructed virtual cycle they use the Sheaves coefficient using as drawing of this Euler class, and what we show is under the cycle map, we prove this goes. For this proof, we need this definition. Okay. And we have another region from Ground theory. So let's assume there is an embedding of P1 into our Calabi-Yau for X. Then, as we've seen, this obstruction theory is governed by X. Let's say this ideal shape side, and this obstruction theory is governed by this II. And using some obvious things. So let's say this is C. So using all this substitutive effect, and this long exact sequence coming from this short exact sequence gives then this is all x. Then the junction set C I. So the precise junction says J. And here the normal number subject is J is exterior power of this. Then in spectral sequence again shows so here you can change by dualizing this, and so this is homology. C. So because now it's moved to here and this disappeared. So what we can observe is, so from this we can observe is x1 I is H0 of normal number. Let's see. And this 2 yi is H1 plus H1 of this theorem. So this is coming from the second exterior power of this is so to understand canonical theorizing circle, and then we apply Z to it. Yeah. So my point is obstruction deformation space of tangent space of these two are same. Like, if you view this as a map, or if you view this as a sheaf I, this are same. And also, so obstruction part says group between obstruction and its sum of its dual gives dt4 obstruction sheaf. So the point is then we must take square root over this obstruction to get to relate this dt and dt. Yeah, that's it.
Questions for Jeongseok?
So that needed a plus outside when you went from the xi with the direct sum, something had to come outside?
That's great. Thank you very much.
No, I mean the direct sum that's inside, the direct sum over j.
Some of
Maybe the next line should have a direct sum.
Yeah,
here.
yeah. Does it have a direct sum outside?
Right. Thank you. Yeah, thank you.
But later you brought it out.
Yeah, so we only see this part. And here actually we must compute.
Right.
Yeah. Here.
So the last part, we related the virtual classes for DT and GW style.
There's some conjecture.
So even for like a numbers, which is invariant.
No, sorry. The conjecture says genetic function cycle. So this we can check this on the reciprocation. Even if you compare with the like elliptic, small elliptic curve, then so you have some more this.
Okay.
So if you had like a cubic form instead of a quadratic form, could you construct a cube root of the Euler class?
I don't think so. So far it's not.
All right, let's thank Jeongseok again.